Welcome back, students. In this video segment, we will begin our segment of our course where we discuss multiple integrals. The section 15.1 is entitled Double Integrals over Rectangles. In order to do this, we need to take a look back into Calc 1 and review the concept of a definite integral. So for the first 5 minutes or so, we're going to look at a review of what it means to have a definite integral. So given a continuous non-negative function y equals f of x, given a continuous non-negative function, let's say y equals f of x, on the closed interval we'll call D, A, B. The fundamental problem in Calc 1 that led to the definite integral was to find the area under f of x lying above the closed interval AB. So find the area under y equals f of x lying above the domain DAB. Okay, I'm going to use some notation though that's going to lead into our three-dimensional case. So in other words, find the area of, let's say, the region R, where R is given in set notation, is the set of all points x, y, such that y lies between 0, the x-axis, and the curve f of x, and the x value lies between A and B. Okay, we'll get used to this notation. It's just a fancier notation of saying the same thing as we did in less fancy notation. Just find the area underneath the curve above the interval from A to B. So let's take a look at what's going on graphically. What I'm going to do is I'm going to draw the area in question. So here's the xy plane, let's say the first quadrant of the xy plane. Here's our function. It's a non-negative function. A non-negative function means that the function lies above the x-axis, and we're interested in the area underneath the function above the x-axis from A to B. And in Calc 1, we cut this into 5 steps. Even though you might not have remembered the 5 steps sequentially, we did do this in 5 steps. The first step was to divide the interval from A to B into subintervals of equal length. So the first step is to divide the interval from A to B into subintervals of equal length, and we'll call that equal length delta x. So delta x will be the length of the entire interval. Remember, the length of an interval from the left-hand endpoint A to right endpoint B is right endpoint minus left endpoint. And we're dividing that by the number of subintervals I'd like. So I want to divide AB into 2 subintervals of equal length delta x. So how many subintervals will there be? Well, the n determines that. So the n is the number of subintervals that we're dividing up the interval from A to B into. So let's actually do that on our drawing. So here's our first subinterval from A to this point. This point here we're going to call x sub 1. The next point will be x sub 2. and we'll go all the way to b, and b we'll call x sub n. Just before that, we'll have x sub n minus 1. And a typical subinterval somewhere in between a and b will have a left endpoint x sub I minus 1 and a right hand endpoint x sub I. So I just drew the number I subinterval, or the ith subinterval. So we divided up the interval from a to b into subintervals of equal length. The next step is to, within each of those n subintervals, pick a point randomly. Pick a point at random. So step 2 is to pick an x sub I star in the ith interval, the number I interval. And what that translates into is to pick an x sub 1 star in the first subinterval, x sub 2 star in the second interval, and so forth. Okay, so I'm going to do that in a different color so our drawing doesn't get too cluttered up. So in the first subinterval, I'm going to pick a point at random. Not the left-hand endpoint or the right-hand endpoint or the midpoint, just some point at random. And I'll pick that red mark point in the first subinterval as that point. I'm going to try to squeeze in a little more room here. Give me a second. It'll work. Let me see if I can do it again. Oops. I'm slowly getting used to this the surface, so bear with me. Okay. So what I'm going to do is, within each of the subintervals, I'm going to pick a point at random. So here's x sub 1 star. In the second subinterval, the selection of the starred x value has nothing to do with what we did in the first subinterval. This is a second random pick of an x value. We'll call it x sub 2 star. We'll keep doing this until we get to a typical rectangle somewhere between the first and the number n rectangle. We'll call this x sub I star, and we'll go all the way to the end, and in our nth subinterval we'll pick x sub n star. Okay, so after we divided up the interval from a to b into n subintervals of equal length delta x, we picked a random point in each of the subintervals. Next, I want to find the area of a typical rectangle above x sub I star. That's going to take a little bit of explanation, so let me just get that down. So I want to find the area. Let me actually clean that up just a little bit. I want to find the area. Find the area of a typical rectangle above x sub I star. So here's what I mean. Let's go back to our drawing. From x sub I star, from that point on the x-axis in the ith subinterval, I want to imagine going up to my curve. This little green dotted line is going directly up to my curve at the x sub I star. And I'm going to form a little rectangle with the height of that rectangle being the value of the function at the x sub I star. Okay, so the area of that rectangle will be f, the value of the function at that starred x value, at x sub I star, that's the height, times the width of the rectangle. And each of the rectangles that we're drawing, and there are going to be n of them, is going to have a width of delta x. Okay, so imagine doing that within each of the subintervals. Within each of the subintervals, I go up to the curve at the starred value, and I form a rectangle. In the second subinterval, I go up to the curve at that starred value, and I form a rectangle of the height, the value of the function at that starred x value, times the width delta x to get the area. And I keep doing that until I get to the end of my domain. At the x sub n star, I go up in green. That's the height of my rectangle. I form a rectangle in red using the height of that rectangle as the value of the function at f of x sub n. Multiply that by delta x. And I'm looking at n rectangles that estimate the area underneath the curve. So the next step then is to estimate the total area of our region by summing up the areas of those n rectangles. So step 4 is sum these areas to estimate the area of our region. And I recall that we're calling our region R. Okay, and we use sigma notation to shorten our notation a bit. So the area, the total area that we're interested in is approximately equal to the sum of the f of x sub I star delta x's as I ranges from the first rectangle to the nth rectangle. I know you're familiar with sigma notation because you spent a great deal of your life on it in Calculus 2 when you talked about series. So hopefully this isn't a big leap for you to use the sigma notation. If it is, review sigma notation. We're going to need it. And then find the exact area underneath the curve by using some calculus. Up to this point, all of what we've done so far can be done using algebra. What I want to do is I want to let the number of subintervals approach infinity. I want to look at more and more and more subintervals. If I do that, the error that's introduced by using rectangles to estimate the area underneath the curve, the error will squeeze out, will get smaller and smaller and smaller as I fit more and more and more of these rectangles underneath the curve or within our region by letting the number of subintervals go to infinity. Find the exact area. Find the exact area by letting n approach infinity. Okay, so the exact area, and this is actually how we define the exact area underneath the curve. The exact area is the limit as the number of subintervals, which equates to the number of rectangles, approaches infinity. So it's the limit of this very famous sum called a Riemann sum, just to remind you. And that's the definition, that is a definition of the definite integral from a to b of f of x dx. Okay, and before we move on to our Calc 3 iteration of this concept, it should be noted that we used area, the concept of area here, only to motivate us our definition geometrically. The integral of a function doesn't have to equal area. In fact, in many applications, possibly in most applications, we're not looking for area with the definite integral. Okay, but if our function is non-negative and our function is continuous, then the integral, the definite integral of a function corresponds to the area underneath the curve, or the area of the region above the x-axis and underneath the curve between a and b. Okay, So let's move on to why we're here. We're here to extend the notion of the integral, the definite integral from Calc 1 into the double integral, and ultimately the triple integral in later sections, the double integral in Calc 3. And we're going to do that by looking at a specific geometric problem. Before we do that, we need some notation. We need some new notation. Okay, so what I'd like you to do with me before we consider the idea of a double integral is to consider the definition or the symbolic notation for a rectangle in the xy plane. So let me see here if I can draw a rectangle in the xy plane. I got pretty lucky. Okay, so here's a rectangle, simply a rectangle. Oops, my luck just ran out. Here's a rectangle in the xy plane. And let's give the rectangle some dimensions. Let's say our rectangle, the projection of our rectangle along the x-axis gives us the interval from A to B, closed interval from A to B, and the projection of our rectangle along the y-axis gives us our region from C to D. We can denote this rectangle R using interval notation. We can denote this rectangle as the rectangle AB cross CD. And the cross is not a kind of we're not interpreting the cross as a kind of multiplication. This is just the notation for a rectangle. The rectangle that I've pictured here in the xy plane. Okay. Okay. So on to our problem. On to our definition of the double integral. So given in the Calc 1 version of the integral, we were looking at a continuous non-negative function. We're doing the same thing here. Suppose we're given a continuous non-negative function. And our function is z equals f of x, y. So our continuous, geometrically, our continuous non-negative function represents a surface. Okay? And this surface is defined on domain R, and the domain R is the rectangle I pictured above, AB cross CD. Okay, the problem is very similar to the problem we looked at in Calc 1. The problem is not to find area, but the problem is to find the volume of the solid, and we'll call the solid S. And I'm going to use the fancy set notation, then I'll state what it means in a more informal way. The solid is going to be composed of the set of all points x, y, z, such that the xy plane is beneath the solid, or part of the xy plane, so z lies between 0, and above the solid, the top of the solid, is the function. Okay, where x and y are elements of that funny little e, the rectangle R. Okay, so in informal terms, I'm looking for, that is, the volume under z equals f of x, y, and above the x-axis. Nope. I slipped into Calc 1 mode there. It's not above the x-axis. It's above the xy plane. lying above the rectangle R. If that doesn't make sense, we're going to draw it. So let's take a look at what this looks like. I'm going to draw this very slowly and methodically. So first thing I need, and I'm going to put our region in our usual position. I'll put it in the first octant. So here's a drawing of our region. Here's the YZ plane. Here's the x-axis coming out. So, and there's my dog is starting to bark. Okay. So, let's take a look at the rectangle pictured above here. Let's look at the rectangle R, AB cross CD, but put in perspective in 3 space here. So here's A along the x-axis. Here's B along the x-axis. Here's C along the y-axis. And here's D along the y. Oops. Go backwards D. Here's D along the y-axis. Okay, so I'm going to draw our rectangle. So our rectangle is going to have a lower edge, kind of above the interval from A to B. Then here's the left-hand edge, if we were staring directly down at it. Left-hand edge. Here's the right-hand edge of our rectangle. Here's the upper edge of a rectangle. So there's our rectangle AB cross CD. And above this rectangle, we have a surface. Above this rectangle, we have a surface. So I'm going to draw the surface. I'm going to make it come pretty high, though, so it doesn't get in the way. We're going to be drawing a whole bunch of stuff below. So we're going up to our surface, up to our surface. Our surface is going to look something like a loaf of bread. Something like a loaf of bread. So I'm going to bring up the Z values along the boundary as high as I can. And here's our surface. So hopefully you can see, or you can visualize with me, a loaf of bread in the first octant. Okay. All right. Now we're going to find the volume of this loaf of bread by doing a very similar thing that we did in Calc 1. In fact, step by step, it's going to mirror exactly what we did in Calc 1. In Calc 1, the first thing we did was to divide the interval from A to B into subintervals. Well, we're going to do a similar thing here. We're going to divide the rectangle R, the base of our region, into subrectangles of equal area. Okay, so that's going to be our first step. So our first step is to divide R into subrectangles, not subintervals, because R is a rectangle itself, so not a line segment. Subrectangles of equal area delta A, and that delta A is going to be equal to delta X times delta Y. And I'll explain where those delta X and delta Y's come from. In fact, right now, the delta X's are going to come from doing what we did in the Calc 1 version. We're going to divide the interval from A to B into subintervals of equal length delta X. And that equal length will be the length of the interval from A to B divided by m. M as in Mary is going to be the number of subintervals that we divide the interval from A to B into. Let's do that right away. Let me see. I think what I'll do is I'll use green to look at the subdivisions here. So here's, let me clean this up just a little bit, make it a little sharper. Here's x sub 1. Here's x sub m, that's B. And just before x sub m would be x sub m minus 1. And somewhere in the middle is a typical subinterval whose left-hand endpoint is x sub I minus 1, and whose right-hand endpoint is x sub I. So I divided up the interval from A to B into n sub m as in Mary subintervals of equal length delta x. I'm going to do the same thing along the y-axis. I'm going to divide the interval from C to D into subintervals of equal length delta y. The delta y is not going to be equal to the delta x. The delta y, generally, the delta y is the length of the interval from C to D, so it's D minus C over, and I'm dividing the interval from C to D into n, as in Nancy, different subintervals of equal length. Let's put those in. I think we'll use the same green. So here's C, right above C is y sub 1, D is y sub n, and somewhere in between C and D is a typical subinterval. The lower endpoint of that interval will be y sub j minus 1, the upper interval y sub j. So we've divided up the interval from C to D into n subintervals of equal length delta y. Now what I'm going to do is I'm going to look at the dividing up R into subrectangles of equal length, and I'm going to draw a typical rectangle. Let's go to the number I subinterval, and then go into our region R in the xy plane, into our rectangle R in the xy plane. I'm going to also go to the number j subinterval along the y-axis, and then move into our interval R, into our rectangle R in the xy plane. And you can see that those typical rectangles along the x and y axis, typical subintervals along the x and y axis correspond to perfectly a sub-rectangle within our rectangle R in the xy plane. Okay. All right. So you're looking at that little green rectangle in the region R. That's a typical sub-rectangle. Okay. That was a big chunk to chew for number one. Step two is to, now that we have a whole bunch of little green subrectangles in our big rectangle. In fact, how many of those rectangles are there? Think about that for just a minute. How many of those little green rectangles are there? I got that typical green rectangle by dividing up the x-axis, the interval from A to B, into m subintervals of equal length, and dividing the interval from C to D into n subintervals of equal length. How many total would there be? Well, we divided up the x-axis into m subintervals, the portion of the y-axis, into n subintervals. So there should be m times n subrectangles. M times n subrectangles. If that doesn't make sense, you can imagine dividing up AB, the interval from A to B, into, let's say, 3 subintervals of equal length, and divide up the region, the interval from C to D, into 2 subintervals. So we have a total of 3 times 2, or 6 subintervals. Let's see. I'm getting better. Slowly. Okay. Our next step is to, within each of these m times n subrectangles, we're going to pick a point at random. In Calc 1, we called that random point in the number I subinterval x sub I star. We can't label the typical point in the subinterval as x sub I star, y sub j star, because the location of that rectangle, that typical little green rectangle, is going to depend, the x and y are going to depend on the subscript I and the subscript j. If that didn't make sense, hopefully this will. We're going to pick a point. We're going to pick a point randomly within each of the subrectangles. That point will have coordinates x sub I, j. The x coordinate will depend on what the I value is along the x-axis and what the j value is on the y-axis, star, y sub I, j, star. So we have a doubly subscripted point in each subinterval, in each subrectangle. I think on my notes I actually wrote subinterval. Okay, our next step is to find the volume of the box that lies above that starred point. So find the volume. Find the volume of the box above x sub I j star y sub I j star. Okay, let's draw it. And when we draw that typical box, I think you'll see how the formula bears out. So let's identify the point, the random point. We'll do it in red. X sub I j star, I j star, y sub I j star. And from that point within a typical subrectangle, I'm going to go up to my surface. I'm going to go directly up to my surface at that point. A little dotted value, green value. So I'm now on my surface. Kind of emphasize it by doing this. And I'm going to use that as the height of that typical box. So I'm going to draw the little typical box whose volume I'm after. I'm going to go up. To, let me see if I can clean that up a little bit. I'm going to go up to the surface. And the distance I'm going to go up to the surface is the dotted vertical line. I'm going to go from each corner of that little green rectangle in the xy plane. I'm going to go up to the surface, same height. What's the height? What is that height? What is its actual formula? What is this height that I'm drawing? What is this dotted height that that green dotted height what is its actual value? Well, the point in the xy plane is x sub I j star, y sub I j star, and z values are given by f of xy, so that height of that one box is f of x sub I j star, y sub I j star. So the volume of that one little box is going to be its height, f of x sub I j star, y sub I j star, times the area of the base. Or if that doesn't make sense, what's the volume of block? This length times width times height. It's delta x times delta y times the height, the z value at that starred value. So that f of x sub I j star, y sub I j star times delta a, that's the volume of that little red column, that one box. I want to estimate the area underneath the surface by doing exactly the same thing in the Calc 1 version. I want to sum these volumes to estimate the volume, total volume of our solid S. Okay, now I have a doubly subscripted value. I'm summing as I ranges from 1 to m, and I'm also summing as j ranges from 1 to n. So I'm going to first sum, I'm going to sum as I ranges from 1 to m, and just before that, I'm going to sum as j ranges from 1 to n of f of x sub I j star, y sub I j star. The order in which I said this might have been a little confusing, so I'll repeat what I said. This is a double sum. Look in the inner portion of the double sum first. In the inner portion of the double sum, I'm going to hold I fixed and sum as j ranges from 1 to m, n as in Nancy. So it's like I'm holding x fixed within that number I subinterval, and I'm summing in the y direction as j ranges from 1 to n, and then I'm finishing up the sum as x ranges in the x direction as I ranges from 1 to m. This sum can be quite large. This sigma notation is really necessary to approximate this, or to write this out. So the volume that I'm interested in, is approximately equal to this value. And the next step is to use calculus. Calculus is only used in the last step. All of this, believe it or not, is just algebra, a whole bunch of algebra. Find the exact volume. Find the exact volume. Find the exact volume by letting the number of subintervals in each direction, the x direction and y direction, go to infinity. So we're going to let m go to infinity and n go to infinity. So the exact volume is actually defined as the limit as m and n go to infinity of this approximate volume of this double sum, this double Riemann sum. I goes from 1 to m, f of x sub I j star, y sub I j star, delta a. And this is the definition. This is the definition of the double integral of the function f of xy dA over the rectangle R in the xy plane. Okay. So we're going to look at a specific example. If you're in the mood for a break, this would be a perfect time to break. And we'll continue right after the break. So let's look at our first example of an actual double integral. So, example, evaluate the double integral of 4 dA over R, where R is the rectangle from -1 to 2 along the x-axis, cross 0 to 5 along the y-axis. In order to do this, we don't need any fancy formulas. We don't need to actually even use that very, very complicated limit of this double sum. This definition is very, very, very complicated. Just as the definition of the double integral or the regular integral was in Calculus 1, the limit of the Riemann sum. In Calc 1, if you had a really good calculus instructor, they showed you how to evaluate a couple of a few definite integrals, and that wasn't before using the fundamental theorem, and that wasn't really easy. So the same thing corresponds here. So the idea in our course is to try to avoid using the limit of the Riemann sum definition to evaluate multiple integrals. However, to be fair to the rest of your careers in the sciences, when you evaluate double integrals, you're going to be using the double Riemann sum definition in practice, just as with regular integrals, single integrals, if you will, from Calc 1. We're only able to estimate the values of double integrals, and we do that by using the double integral definition. Okay, so let's solve this problem. Let's try to evaluate the double integral of 4 dA. Now remember, we motivated the definition of the double integral by considering a non-negative function z, and that's happening here. Z equals 4 is as a constant non-negative value of 4. So we can interpret this double integral as volume. We can interpret this double integral, the value of this double integral is the volume under z equals 4 and above the rectangle R. So what we're looking at, well, what does the solid look like then? If its base is a rectangle and its height is a constant 4, then we're looking at the volume of a box. Okay, and the volume of a box is nothing more than the length times the width times the height of the box. If that doesn't make sense, take a quick look at what this thing looks like. So here's the first octant. We need to extend the x-axis a little bit backwards, since I'm going from -1 to 2 along the x-axis, and from 0 to 5 along the y-axis. Let's say this is 5 along the y-axis. Okay, here's the axis. So our base is the rectangle pictured. That's the base of our solid we're using to interpret our integral. The height is a constant 4. So here is our solid. Our solid is simply a box. The volume of a box is length times width times height. So this double integral of 4 over the rectangle R is nothing more than the height of the box times the length of the box. The distance between -1 to 2 is 2 minus -1 times the width of the box. The distance between 0 and 5 in the y direction is 5 minus 0, or 4 times 3 times 5, or 60. I'm not putting units on this because even though we interpreted this integral as volume numerically, there was no statement in the problem that this was a volume problem. So numerically, we get the volume of a box whose base is formed by the rectangle R and whose height is 4. Okay, so here's our first formula. This sort of motivates our first formula. So if f of xy is a constant k, let's say constant, then the integral, the double integral over a rectangle R of f of xy dA is going to be the height of the box times the area of the rectangle R. So times, well, I didn't define R, so, and R is the rectangle AB cross CD. Then the integral is the constant k times the length of the box, b minus a, times the width of the box, d minus c. Okay, so specifically putting in k, the integral of k is equal to the constant k times the area of the box. In practice, this almost never happens. In practice, it almost never happens that the height of our function is actually constant. So how do we evaluate double integrals over rectangles when the height of our surface is not constant? That's our next idea to look at. And it's kind of amazing. It's amazingly simple how we do this. So remember, the idea is to avoid using the Riemann sum definition of the double integral as much as possible for us. The idea is that we somehow develop a quote-unquote easy way to evaluate these complicated quantities like integrals. In Calc 1, it was called the fundamental theorem of calculus. We're basically going to be extending that idea here to integrals over rectangles of non-constant functions, or constant functions, but generally non-constant functions. So in order to do this, I'm going to need my surface again. So I'm going to draw my surface. I would pause this to do it, but I think might be a good idea for you to actually see these surfaces drawn. You're going to be doing a lot of drawing in this chapter. So again, I'm drawing my surface, or my solid, that lies above the rectangle AB cross CD. Okay, so first I'll draw the rectangle in the XY plane, AB cross CD. So here's A, here's B, along the x-axis, along the y-axis, here's C, and here's D. Okay, axes in there. So I'm going to draw the left edge of my rectangle in the XY plane. Here's the left edge. I would like to clean that up just a little bit. I didn't really clean up very much. Okay. I may have to just accept my drawing. So here's the left-hand edge. Here's the bottom edge of my rectangle now. Bottom edge parallel to the x-axis. Here's the right edge, and all these dimensions I'm giving you are as if we're looking down on the rectangle. Here's the top edge. So there's our rectangle R, just as before. And above this rectangle, we have our surface given by z equals some function of x and y. I'm going to go high enough so the top of the surface doesn't get in my way. Okay, going up. Going up. And here's our loaf of bread again. Here's our loaf of bread. I want the volume of that loaf of bread. But I'd like to avoid using the Riemann sum definition that we had. So the height of the loaf of bread is z equals f of x, y. I'm going to continue on this loaf of bread analogy here. Basically, we're going to find the volume of this loaf of bread by finding the volume of one slice of the bread and then adding up the volumes of each of the slices to get the total volume of the loaf of bread. Okay, so let's slice this bread. Let's slice this loaf of bread by putting a knife through the bread parallel to the YZ plane. Okay, so I'm going to cut parallel to the YZ plane. I'm going to slice at X. I'm going to slice through the loaf. So here's our slice. Okay, here's our knife slice. Well, I want to give this some dimension, and I'll do that in a minute. All I've done is I've sliced through the loaf of bread. I'm going to come forward from x a little bit, a distance dx, and we'll slice again to get an actual three-dimensional volume slice. So for now, there's a picture of one edge, the back edge of our slice. Okay. So what's the area of that slice? What's the area of that slice? Well, that slice can be thought of as the area that's underneath the curve formed by the top of the slice, and the top of that slice can be placed in the YZ plane. If you missed that, I'm actually going to draw it. Let's draw a little picture off to the side here of that slice, but placed in the YZ plane. So here's the YZ plane, and here's that red slice. I'm pushing it back into the YZ plane. Okay, C to D. The top edge of the slice is given by the z value in our function, where x is held constant. If we hold x fixed, hold it fixed at the red fixed value along the x-axis, then the resulting function will be a function of y alone. So that's the equation of the top of that slice. And I'm going to use calculus 1 to find the area of that slice. The area of that one slice, let's say a slice, is, what's the area from Calc 1? It's the integral of the function. It's the integral of the function. The function depends on y, as y varies from c to d, where x is held fixed. So when we interpret this integral that I just drew, we have to assume that we're holding x fixed at some value. It's sort of like a partial derivative with respect to y. Sort of. In fact, you can regard this as sort of like a partial integral with respect to y, holding x fixed. So that's the area of the slice. So what's the volume of the slice of bread? Well, as I mentioned, in order to get a slice of bread, we're looking at a three-dimensional picture. So we're going to increase x a little bit. So here's x plus a small amount dx, and we'll slice through the loaf again. And when we do that, we're looking at a slice of bread, as if we were making a sandwich. Here is one slice of this loaf. I want the volume of that red slice, that three-dimensional red slice of bread. That volume is nothing more than the area of the face of the slice times its width. So the volume of that one slice is nothing more than the area of the slice times dx. But the area of the slice is the integral from c to d of f of x held constant y, integrate with respect to y, and then multiply that by dx. Okay, now here's the question of the ages. How do I get the total volume of the loaf of bread? By adding up all the volumes of all the little slices of bread that make our individual sandwiches. So the total volume I get by adding up, integrate, all the areas of the slices times the dx's, all the individual slices of bread as x varies from a to b, or integrate from a to b of the integral of f of x held fixed y with respect to y from c to d, and integrate that result. Now x is not fixed, x varies from a to b. It looks like I formed something like the double integral. This last quantity is not called a double integral. This last quantity is called an iterated integral. An iterated integral. It is not a double integral. It looks so much like a double integral, though, that professors, students alike will call this integral a double integral. It is an iterated integral. By iterated integral means we evaluate the inner integral with respect to y, single integral, and then we evaluate the single integral of that result with respect to x from a to b. So the net result here, so let's call this the big result for right now. It's actually pretty big in the scheme of things. The big result is that the double integral of a function f of xy dA over a rectangle R is equal to the iterated integral of f of xy, first with respect to y and then with respect to x, as y varies from c to d, and then integrate that result as x varies from a to b. Okay. Now this was the result that we get by slicing our loaf parallel to the yz plane. If we decide to slice our loaf parallel to the xz plane, then the order of the integration will be reversed. So this is the same thing as the integral first between a and b of our function with respect to x, and then integrate that result from c to d with respect to y. So the order in which we evaluate iterated integrals when we're integrating over a rectangle is unimportant. Okay. Later on, in fact, in our next lecture, we're going to be integrating not over a rectangle in the xy plane, but over arbitrary closed regions in the xy plane, and we can't just flip the orders of integration around. But for now, we can. If we're integrating over a rectangle, then the order in which we evaluate our iterated integral is unimportant. Let's take a look at a really important example to illustrate this. So for this example, we're going to look for a volume. Okay, so our next example, very, very important example. So our example is to find the volume. Find the volume of the solid S, capital S. S, where, say comma, where S is composed of the set of all points in 3 space in R3, such that the xy plane is below us, the paraboloid z equals x squared plus y squared is above us, and x and y lie in a rectangle R, with the rectangle R being the rectangle 0 to 1 along the x-axis, 1 to 2 along the y-axis. Okay, so to get an even better idea of what's going on here, I'm going to make my best attempt at drawing this. So bear with me. Okay, so we're looking at the volume captured. Already I don't like my drawing. We're looking at the volume captured above by a paraboloid. I'm going to try something tricky here. That was nice. I think my luck's going to run out here. So, okay, so here's the z-axis. Coming down. Already my z-axis looks horrible. I'm not going to get it to look any better. Oops. Too much coffee, like usual. So here's our paraboloid. So let's get an idea of what our, if we can, of what our actual solid S looks like. Along the x-axis, we're looking at 0 to 1. Along the y-axis, we're looking at 1 to 2. So the base of our solid is, let's see if I can make this better. Base of our solid is this little rectangle from 0 to 1 along the x-axis, 1 to 2 along the y-axis. Above is our solid. So above is our solid. So if I can pull all this together, we'll see. So I'm drawing the top of our actual volume. Let's see. I think that actually works out. You know, it only works out if you can see it too. So this, what I'm drawing now is the top of our, is where the top of our solid lies. Let's see if I can do this. So this is actually on the paraboloid, and above are in the xy plane. So the top of our solid is not horizontal, but it's a little patch of the paraboloid. Okay, so let's get this volume. So the volume is the double integral, as long as our function is non-negative, and then it is the double integral of our function x squared plus y squared dA over the rectangle R. But our result a couple of minutes ago said that we can convert this to something we call an iterated integral. That is, we can translate this into sequentially evaluating an integral first between 1 and 2, and then between 0 and 1 of our function x squared plus y squared. When we integrate from 1 to 2, that's in the y direction, so we're integrating first with respect to y, and then integrating that result from 0 to 1 with respect to x. Let's actually do this. Let me see if my surface will allow me to move. I did. With the help of one of your classmates, I'm able to do this. I don't want to destroy his anonymity, though, so I'm not going to tell you who showed me how to do this. Okay, so let's evaluate this iterated integral. We first integrate with respect to y. That means we're holding x constant, just like in partial differentiation. So we're going to integrate between 0 and 1 later, but first we're integrating x squared with respect to y. Well, if I'm holding x constant, then x squared is constant. The integral of constant with respect to y is constant times y. The integral of y squared with respect to y, on the other hand, is 1/3 y cubed. And that is as y is carried between 1 and 2, and then I integrate that result with respect to x. Okay, so let's keep going on this. I'm integrating between 0 and 1 afterwards, but right now I'm substituting y equals 2, so 2x squared, and y equals 3 into 1/3 y cubed, so plus 8/3. And then the fundamental theorem of calculus, evaluate the same expression with y equals 1 and subtract. So 1 times x squared plus 1/3 1 cubed times 1 cubed, which is 1/3. Then I'm integrating that result with respect to x. So this is how an iterated integral plays out, first with respect to y and then respect to x. So now we integrate this with respect to x. Let's simplify this a little bit. 2x squared minus 1x squared is x squared. 8/3 minus 1/3 is 7/3. I'm integrating this with respect to x. Simple integral. Antiderivative of x squared, 1/3 x cubed, and antiderivative of 7/3 is 7/3 x. This is carried between 0 and 1. At 0, we get no contribution. At 1, we're just looking at 1/3 plus 7/3. The result is 8/3. 8/3. I'll clean up my 3 while you think about what kind of units we have. 8/3 what? It's volume. Cubic units. Cubic units. If you said cubic units, you were right. Okay. Now I have one more example to end our section. Excuse me. Okay. I mentioned earlier, and I'm going to refer us to that part of that lecture. I mentioned earlier in our lecture, not too much earlier, about 10 minutes ago, that we had a big result that said as long as we're integrating over a rectangle, that our double integral can be converted into one of two iterated integrals. Excuse me. And it doesn't matter what order of integration we perform. This integration for the iterated integral. Now, the end result, the value will be the same regardless of whether we integrate first with respect to y or first with respect to x. The computations along the way can be very, very difficult. Excuse me. In fact, your choice of the order of integration can often lead to an impossible situation where a particular choice of the order, say first with respect to x and then with respect to y, can produce a difficult or impossible situation, whereas reversing the order of integration would produce something that's possible or even simple. Let's see how that actually happens. Let's take a look at for our last example, evaluating evaluate the double integral of x times the cosine of x times y dA over R, the rectangle R, where R is the rectangle between 0 and pi over 2 along the x-axis, cross 0 to 1 along the y-axis. Okay. We actually don't need a picture of the region, which is good because I am not familiar with how to graph x cosine of xy, and neither do you have to be. So I'm gonna evaluate or attempt to evaluate this double integral by integrating first with respect to x and then with respect to r. So the double integral of x cosine of xy dA is, by our big result, the integral as of x times the cosine of xy, first with respect to x, as x varies between 0 and pi over 2, and then with respect to y, as y varies between 0 and 1. Perfectly legitimate to do this, to set up the integral this way. Now, let's concentrate on how this integral plays itself out. The innermost integral says that we're integrating with respect to x. In order to do that, I'm going to integrate by parts. The live variable is x when I integrate with respect to x, so I'm holding y constant. So I have something that looks sort of like integrating x times the cosine of 5x. But we don't have 5x. Y is the constant value. So I'm going to integrate by parts, or attempt to integrate by parts. I'm going to let u equal x, dv equal the cosine of xy with respect to x, okay, so that du equals dx, and we need to find v, so we need to integrate cosine of xy with respect to x. So y is held fixed. If it were cosine of 5x, the integral would be 1/5 sine of 5x. Well, it's not 5x, it's yx, so it's 1 over, not 5, but 1 over y, the constant, sine of xy. Okay, fair enough. So we're looking at the integral from 0 to 1, and here we're integrating by parts of u times v. So u times v will be x over y times the sine of xy. Now this is a definite integral, so this is as x is varying between 0 and pi over 2. We have to keep track of that. Minus the integral of v du. Well, when we're integrating with du is actually dx, we're integrating with respect to x, so y is held fixed. It can be factored outside of the integral or left inside. Times sine of xy with respect to x. Okay, then we integrate that result with respect to y. Keep in mind that we're integrating the innermost integral first. Okay, so let's proceed with this. The integral from 0 to 1. If x equals pi over 2, it's getting a little complicated looking, but not too bad. Pi over 2 over y, sine x is pi over 2 again, pi over 2x. At x equals 0, we get 0 as a contribution. Except this x is a y. Okay. And continuing on, let's see, no, I got lost here. The second integral, the integral of sine is negative cosine. So if they were the integral of sine of 5x, it would be negative 1/5 cosine of 5x. So it's not 5x, it's yx. So it's plus 1 over y squared, the 1 over y that was already there, then another 1 over y from our integral, the integral of sine negative cosine of xy as x varies between 0 and pi over 2, then this result is integrated with respect to y. Okay, so one more step here. Integral from 0 to 1 of pi over 2 over y times the sine of pi over 2y. And substituting x equals pi over 2 into the second term there, I have 1 over y squared cosine pi over 2y. And at 0, cosine of 0 is 1, so minus 1. All of this with respect to y. Now, good news and bad news. The good news is we don't have to go any further. In fact, the bad news tells us why. This is impossible. This is impossible. The first integral, actually the first and second integrals, they're both impossible. This is impossible. Impossible to integrate using the fundamental theorem. It's absolutely impossible to integrate the sine of a constant times y over y. This is impossible, cannot be done. Now, to end this example, I want to reverse the order of integration. So, reversing the order of integration, let's see what happens. So we're still looking at the same integral. It's a double integral over the region or rectangle R of x times the cosine of xy dA. But I want to integrate first with respect to y and then with respect to x. X times the cosine of xy, first with respect to y and then with respect to x. So y varies between 0 and 1 in our rectangle, and x varies between 0 and pi over 2. We just switch the limits of integration again. Remember, you can switch the limits of integration when you switch the order of integration, when and only when you're integrating over a rectangle. Now let's see what happens. Let's take a look at the inner integral in this iterated integral. We're integrating now first with respect to y. That means x is held fixed. X is constant. So the x in the first integral is constant. It factors out of the integration process. We're just integrating the cosine of xy with respect to y. That's simply 1 over x times the sine of xy. And then that's carried as y varies between 0 and 1. Then integrate that with respect to x. My goodness, look at this. This is the integral from 0 to pi over 2 of the sine of xy with respect to x. When I substitute y equals 1, I get the sine of x. The 1 over x and x cancel. At y equals 0, I have the sine of 0 is 0. I'm integrating nothing more than the sine of xy with respect to x between 0 and pi over 2. The integral sine is negative cosine. So this is negative cosine. Oops, in fact, I made in my haste to get something simple here, I've got something that's not even part of our problem. Hold on a second, let me clean this up a little bit. Okay. So substituting y equals 1, I get sine of x with respect to x. Integral sign is negative cosine from 0 to pi over 2. Cosine of pi over 2 is 0. So this is minus cosine of pi over 2. Minus a minus, so plus cosine of 0. The cosine of pi over 2 is 0. Cosine 0 is 1. Look at what happens when we reverse the order of integration. This doesn't always happen. Sometimes when you reverse the order of integration, you still have an impossible situation. But for you guys, very often, and I think in several, at least a few places in your homework, when you reverse the order of integration, you go from something that's either difficult or impossible to something that's not only possible but simple. And that ends our lecture on section 15.1, double integrals over rectangles. And I look forward to talking with you all again soon.